Hello and welcome to lesson 7.3. I'm going to try to do this all in one video. I know that last lesson with 7.1 and 7.2 was a little long, so I'm going to try to make up for that and make this one as short as possible. Okay, today you're going to use functions involving e. You will study functions involving the natural base e. Okay, so what is this natural base e? The natural base e is irrational. It is defined as follows: as n approaches positive infinity, 1 plus 1 over n, all raised to the nth power, approaches e, which is approximately 2.718281828. So we're going to simplify some expressions. So if you have e squared times e to the fifth, remember you just apply the properties of exponents and you add your exponents together since you have the same base, and you end up with e to the seventh, and you can leave your answer in terms of powers of e. So that's all you have to do. 12 e to the fourth divided by 3 e to the third. You divide your coefficients to get 4, and then since you have the same base, you just subtract your exponents. So it's 4e to the 4 minus 3, which is 4e to the first, or just 4e. 5 times e to the negative 3x squared. So since 5 and e to the negative 3x are multiplied together, we're going to square each of those bases separately. So we've got 5 squared and then e to the negative 3x squared. 5 squared is 25. For e, you've got a power to a power, so you multiply. Negative 3x times 2 is negative 6x. So that negative, remember, that just means use the reciprocal. So we've got 25 times 1 over e to the 6x, which will give us 25 over e to the 6x. All right, you want to be able to use your calculator to evaluate natural base expressions, so go ahead and grab it. Your e to the x key is on the left column, so find that. So you're going to select the e to the x key. You're going to type in a 4 for that exponent in that little box, and then press enter, and you should get 54.59815,003. And do the same thing for e to the negative 0.09. Press enter, and you should get 0.9139311,853. Okay, natural base functions. A function of the form y equals a times e to the rx is called a natural base exponential function. If a is greater than 0 and r is greater than 0, the function is an exponential growth function. If a is greater than 0 and r is less than 0, the function is an exponential decay function. Okay, so we're going to graph these. Let's graph, and then we're going to state the domain and range. So let's graph y equals 3 times e to the 0.25x. Because a equals 3 is positive and r equals 0.25 is positive, the function is an exponential growth function. So that means it should go up to the right. Plot the points, yes. We're going to plug in x equals 0 and x equals 1. If you want to plug in x equals negative 1, that's great too. And that gives us the overall shape, and it gives us 2 points to anchor it. We use what we know about the overall shape to draw it in. So our domain, like any exponential growth function, is all real numbers. We haven't translated to the left or right or up or down, and because we haven't translated up or down, our range is still y greater than 0. Let's look at an exponential decay function. We have y equals e to the negative 0.75, since that's r and it's negative, I know it's going to be exponential decay, times x minus 2, and then plus 1. All right, just like before, we're going to graph the function without the translation first, and then we'll actually look at this and go, okay, it's x minus 2, so that's 2 units to the right plus 1 unit up. So A is 1, and that's positive. R is negative 0.75, like I said, so the function is exponential decay. And then we will sketch a graph of y equals e to the negative 0.75x, and then we'll just translate it 2 units right and 1 unit up. So again, if you don't have 2 different colors of pens or map colors or something, you can just dash in your beginning curve, and then after you translate it and get your final curve, you can draw it in with a solid curve. So if you plug in, and on this one they went ahead, they plugged in negative 2. That's fine. You can plug in any value you want for x, and so you get 4.48. And then they plugged in 0, and so they got 0, 1. They could have also plugged in 1, since that's what they usually do. But what they did was they just used the general pattern. Okay, for exponential decay, you know it's going to approach the x-axis asymptotically. It's going to have an asymptote at the x-axis at the line y equals 0. And then from there, you're going to move to the right 2, because it is x minus h, so h is positive 2, so we move 2 to the right. And then we have plus k, so k is 1, so we'll move up 1. So we move each of these 2 to the right and up 1, and we get our final graph. Okay, so again, no restriction on the domain at all. Okay, so our domain is going to be all real numbers. We've shifted up 1, so instead of the range being y greater than 0, it's going to be y greater than 1. Okay, so we want to consider a real-world application, and this is for continuously compounded interest. We saw that if we held everything constant and we increased the number of times per year that interest is compounded, you get a little bit extra interest. So what would happen if we compounded it all the time? Another way of saying that is that we compounded it continuously. Well, we actually have a formula for that, and it involves this natural base. So when interest is compounded continuously, the amount A in an account after t years is given by the formula A equals P times e to the RT, where P is the principal and R is the annual interest rate expressed as a decimal. So again, you don't need to memorize this, you just need to learn when to use what. So if it says compounded continuously automatically, this is the formula that you're going to use. If it tells you quarterly, monthly, daily, any of those, then you want to use the other formula that we learned previously. Okay, so you deposit $4,000 in an account that pays 6% annual interest compounded continuously. So you want to use the formula with E if it's compounded continuously. What is the balance after 1 year? All right, so we're going to use our A equals P times e to the RT formula. We're going to substitute 4,000 for P, 0.06 for R, and 1 for T because we're interested in just 1 year. So use your little calculator and you get that it is equal to approximately $4,247.35. Okay, so that is E, and you're going to get lots of opportunity to practice working with E. Hopefully you'll get really comfortable with it real soon. So I'll see you in class. Do those problems to try on your own, and come ready to check them and to get busy on your rounds. Have a good day.